Good morning, everyone. So, as you can see, today's topic is radiation. It's a part of heat transfer. The three ways heat transfer can take place: conduction, convection, and radiation. And radiation is a form of heat transfer which does not require medium, and we know that radiation heat transfer takes place in form of EM waves. This is also called EM radiation. And there are certain things we need to understand with relation to radiation. One is something like emissive power. Emissive power is energy radiated per unit area per unit time. This is somewhat it is radiated, so don't confuse with something called intensity. And this is at the source. This is something. So if we have an object, just imagine. So two things we can imagine here: emissive power. If it is a sphere, it's if it is sphere of radius r, and it radiates energy. This is the power of the source. Power is energy radiated per unit time by this source here. So in this case, emissive power will be equal to total energy radiated per unit time, that is P, divided by 4 pi r square. That is emissive power. So that is emissive energy radiated per unit area per unit time, and this is at the source only. And there another term here in relation to this emission, and there's something called absorption also. If we talk about something like sun has emission and Earth absorbs emission. So here this term also is slightly misleading. So just be a little attentive about this particular part here. This is related to emission, this is related to absorption, and this is called absorptive power. Absorptive power, the term used is power, but actually this term is a ratio. It's a ratio of two things. So what does this ratio mean? So at a certain place, you can just imagine, even on the surface of Earth or anywhere, some radiations are coming in. And when the radiations are coming in, irradiations are coming in form of EM waves here. If we keep two objects here, two identical objects, if we keep one is a perfectly black body, PBB, and other is another object for which I want to find out what the absorptive power is. Okay, so what happens in case of perfect black body? Whatever is incident, whatever radiations are incident, it absorbs everything. So that is for energy absorbed divided by energy incident here. So whatever energy which is falling, nothing gets reflected. That is perfectly black body. Whereas other cases, what happens? Whatever energy is incident, part of it is reflected, part of it is absorbed here. So here, so what is absorptive power? Energy absorbed divided by energy incident. So it could be something like if it is 0.9, it means 90% of energy which is falling onto the object is absorbed by the body. So this another term. So this first thing need to answer. Though these two terms sound similar, this is different and this is different. This is third term which is similar is called emissivity. And this is something that's not very often used. Very often we use something this term here. What is emissivity? Emissivity means if you find emissivity of any object, conceptually, how do you find emissivity of an object? This is object for which I want to find out emissivity. I have to compare with the perfectly black body. So there's two identical shape. They're identical shape. This is perfect black body, and both are heated to the same temperature. So except for the nature of the body, everything else is identical. So this will have some emissive power at a particular temperature, and this also will have emissive power, black body, and the ratio of the emissive power is called emissivity. So what is Kirchhoff law here? See, in this case, suppose a body here which absorbs only 50% of incident radiation. So it is absorptive power will be equal to zero point 0.5. If object absorptive power is 0.5, its emissivity also will be 0.5. So if it absorbs 50% radiation, it implies compared to a perfect black body at same temperature, whatever heat is radiated by perfect black body, it will radiate only same proportion. So basically, E is equal to A. That's Kirchhoff rule. So now coming to this a basic definition, and whole topic is about heat transfer. Heat transfer basically means two things may happen. It may absorb, it may radiate. There's something, it's all governed by Stephen Boltzmann law. What is power radiated by an object? Power radiated will be actually emissivity into total surface area. Power radiated is equal to, these are the terms related to power radiation. The power radiated is, first of all, it is fourth power of its temperature. So any object, when we talk about EM radiation, radiation power radiated is fourth power of temperature in Kelvin. And of course, it is proportional to area. There is a constant of proportion is Stephen-Boltzmann constant, and this term E here depends on nature of surface. If you have so that's what very simple formula, and E is equal to absorptive power, and here this is a constant. It's Stephen-Boltzmann constant SI unit, and this is independent of temperature of surrounding. So this is important point to understand. So if we have an object here which is at temperature T Kelvin, and if it is kept in a room which has a temperature of say 27 degrees centigrade, and same object at temperature T, temperature is same, it's kept in a different chamber where temperature is 127 degrees centigrade. So will the heat radiated or power radiated differ? No. Power radiated is independent of surrounding. In both cases, irrespective of what the surrounding temperature is, power radiated depends on the temperature of the object alone and its property, area property and also is independent of temperature of the surrounding. So, but when we keep in this room here and this room here, our radiated will be same. But here it is in contact with the air, which is at 27 degrees centigrade. And here also we'll talk about all the temperatures in terms of Kelvin, which is equal to 300 K, and this is equal to 400 K. So does surrounding make a difference? Surrounding does not affect the rate of heat radiation, but it affects the rate of heat absorption. So when anything which is placed in the surrounding, which is not at 0K, and 0K is possible only when it is vacuum. In case of vacuum, there's no surrounding air molecules, so there's no temperature here. So energy absorbed, it depends on not on the temperature of object, it depends on the temperature of surrounding. So both are independent of each other. One depends on radiation based on the temperature of object, and absorption based on temperature of the surrounding. And energy absorbed here, I could have used term A here, but since A is equal to E, directly I have written E. E times area into Stephen-Boltzmann constant. And this is the temperature of the surrounding, fourth power of temperature of the surrounding. And this is it. So when if any object is placed, so any object will be at a temperature greater than 0 K, and surrounding also will be greater than 0 K. So in any normal scenario, both the things are happening simultaneously. It is radiating also, it's radiating heat, and it's absorbing heat also. What is the net loss of thermal energy? See, when we talk about net loss, we already assume the temperature of object is greater than surrounding temperature. In that case, this temperature, this will be higher, heat radiated is higher, and absorbed is lower. And that's why it will lose net heat, net rate of loss of thermal energy. Net rate of loss of thermal energy is this. And since it is losing heat here, it is something like this delta Q. It loses heat, which will be equal to the rate at which heat is lost, power into delta T. This will lead to change in temperature. That's what we'll understand here. So whenever that's the reason why objects cool down. So whenever object is placed in a surrounding, so if object temperature is, if this object here, if object temperature is object is placed in a surrounding where T is greater than TO, it will lose heat and it will cool down, and in thermal equilibrium both will come to the same temperature. Okay, so net loss of heat in form of radiation will lead to decrease in temperature of the object. So let's take time interval dt. This is the rate at which heat is lost. So and heat lost in time dt will be equal to this. We have taken a small time interval as the temperature can be treated to be constant. Even the temperature of object also, it is changing with time, but a small time interval, the temperature is taken constant. So this is the heat radiated in time dt. And this heat radiated is equal to, since the heat is radiated, it will lead to change in temperature, mc delta theta. Here we are using capital T to indicate, small t term indicates time, capital T indicates temperature. Why is the negative sign here? The dt will be negative here. So this will lead to this the equation. Negative indicates decrease in temperature with time. So this is how the temperature of object is related to this temperature of the object, rate at which this temperature will change. D capital T by D small t will indicate rate of cooling. Okay, so what is rate of cooling? This term becomes rate of cooling, and if we rearrange the term, this is the arrangement of rate of cooling. So that's the rate at which temperature of the object will change. It depends on this difference, this ratio. It also depends on mass on heat capacity. So this also will keep in mind. So basically rate of cooling, if I look from this equation, is proportional to A divided by MC is proportional to A by MC other than surrounding. So if there are two objects which are placed which are identical temperature, so if the temperature of two objects are similar, they are placed in identical surrounding, what is the rate at which they will cool two different objects, other parameters being equal? So that rate of cooling is proportional to A by M by C, or we could have also written mass also is proportional to volume, is proportional to A surface area divided by volume divided by specific heat capacity. What is C term here? It's specific heat capacity. So this is something, and this is typically what we use in case of solving equation. And then based on the previous equation, this slightly modified form, which is Newton's law of cooling. So Newton's law of cooling come from the same equation. The equation is same. Newton's law of cooling is a kind of approximation. So what is the approximation made, and what is the condition under which Newton's law is applicable? It start from the same equation. It's the rate of cooling here. And if I use the term rate of cooling, I can remove the term negative. The rate of cooling itself implies negative. So this whole term is rate of cooling. So what we have done here is what is based on what is Newton's law of cooling based on. We assume the temperature of the object is higher compared to temperature of the surrounding by term delta T. This is a difference in temperature between the object and the surrounding, and object temperature is higher than surrounding temperature. This is based on approximation delta T. Difference in temperature uh, divided by value of temperature of the object is much lesser than 1. Let's try and understand what does it mean. Suppose we take here, and that's something I think sometimes could be a little misleading. Let's say if object is temperature is equal to object temperature is 47 degrees centigrade. So object temperature will not write at 47, we write at 47 degrees. We deal with Kelvin here. So with this temperature, object temperature is 320, and the surrounding temperature is 27, which is 300. So if we write these values here, what is delta T in this case? Delta T is 20. So even delta T of 20 and 30 also, if I take the ratio, which I don't have divide, I need to divide this delta T 20 by this value capital T or T naught. If we divide 20 by 300, it becomes much less than 1. Since even a temperature difference of 20, 30, 40 degrees centigrade also between object temperature and surrounding temperature also, this ratio is small. Hence, Newton law is applicable even for temperature difference of order of 30, 40 degree also. Newton's law of cooling is applicable. But of course, it will lead to, if the difference goes larger, it will lead to some error also. But in most cases, we take that one. And whenever questions come, they do mention whether Newton's law can be taken as valid or not. So that's assumption. Let's look at this is valid. So we can write here this temperature, this T4, writing in terms of surrounding temperature and difference in temperature. So this is what T is equal to T naught plus delta T raised to power 4. Okay. And this term we can simplify. This is something, how do you simplify? What is the approximation here? If I take T naught as common here, if you take T naught out, T naught 4 comes out, it becomes 1 plus delta T by T naught raised to power 4. And this term is much less than 1, so I can use approximation. So if I use approximation, it becomes equal to T naught raised to power 4, 1 plus 4, and this power comes in here, delta T by T naught. And I will multiply, I get this number. So basically derivation is not important, but we're just looking at this kind of approximation is useful many other cases also. So this T4 can be written as T naught and delta T. What we have done here, we have written temperature of the object in terms of the difference in temperature and surrounding temperature. And we put it back here. When we put it back here, it comes in this kind of format here. So in this format, what we notice here, this is not changing. The term changing is delta T. What we understand from a rate of cooling is proportional to difference in temperature. Okay, it is proportional to difference in temperature, delta T. And second thing, the whole equation could be written as this is something will come to later. And other thing, what is the rate of cooling is also proportional, as we talked about, is proportional. Sorry, you can write as A by MT. That's what it is proportional. So rate of cooling, if see, as the temperature changes, all these parameters are not changing. So all the parameters which are not changing, I can treat as constant. So rate of cooling, only thing which changes with the passage of time, delta T will keep changing. So I can take delta T. So basically delta T remains same. So rate of cooling, rest all is taken as a constant. So what is the constant is composed of cost of all those other terms are cost of part of a constant. TEA, sigma, T to T naught raised to power CMC, all are replaced with K. So rate of cooling is K by K into T minus T naught. That's the Newton's equation. And what is the term T here? T is temperature of the object. This is delta T. So this is the temperature of object here. What is temperature of object here? Most cases, what is given? Temperature at the beginning of time interval, temperature at the end of time interval. So this T here is nothing but average temperature of the object. So I could have also written, see, this is something you understand here. You can also write as T. What is T here? Is nothing but average temperature of the object minus T naught. That is Newton's law of cooling. Fairly simple. So two equations. One is net heat transfer rate, net rate of loss of heat. It leads to, there is a loss of heat. It will lead to change in temperature of the object. And if temperature of object is higher, it will lead to rate of cooling. Rate of cooling, we understand this is a rate of cooling without any approximation. With Newton's approximation, this is the rate of cooling proportional to A. Okay, rest all is simple application of the same. Okay, so let's read this question here. A solid sphere and a hollow sphere of same material, equal radius are heated to the same temperature. So we just imagine here the question, what does emotion say? So we have one solid sphere, and both have the same material. If material is same, this is solid material, and this one is a hollow sphere. So this one is a hollow sphere. And if they are of the same material and same object, both are have same radius, both are at the same temperature. Both are the same radius, and both are at the same temperature. So let's understand what would happen. So if they are at the same temperature, what we notice here, this is a rate of radiation. Will the rate of radiation of heat, will it be same or different in these two cases? Rate of radiation in heat is equal to what? Is equal to property of the material. What is the nature of surface? And area into T. What in it is both the sphere, one is solid, one is hollow. But the solid and hollow part doesn't affect. Rate of radiation depends on the outer surface area. Outer surface area is same. Both will have same rate of radiation. Now let's understand what will happen to rate of absorption. If it is placed in some heated same temperature, it is placed in some surrounding. What is rate of absorption of heat? Will that be same or different? Rate of absorption is very similar. This is also is sigma A and T to power 4. This is also similar. So both of them, if they are placed, the rate of loss of heat is equal. Rate of loss of heat is equal. Or rate of loss of heat in form of radiation, they are equal. Will the rate of cooling be same? So dq part is the power is same, but rate of cooling also depends on what are they. So why would they cool at a different rate if same amount of heat is taken away in both cases? In small delta T, same amount of heat is taken away. If same amount of heat is taken away, here the heat taken away is from larger mass, here the heat taken away from the smaller mass. Since the mass is smaller, it will have greater drop in temperature. That's why it will cool faster, it will cool slower. So rate of cooling, yes, net rate of heat loss is same, but since the mass is different, and hence, and that's why again, if we look at this, what are we talking about? Rate of cooling, dt by dt is proportional to A by mc here. So which part is different? This is also same, this is also same, this one is different. So one which is smaller mass will have faster rate of cooling. And if I draw a figure, same thing I have to represent in terms of a figure here. Only thing we can predict if one side, if we have temperature T, and other side, this is time at one side, and temperature other side. Initially, both are at the same point, but one will go like this and other will go like this. Which one of the graph will represent solid sphere and which will represent hollow one? The one which is steeper slope will represent hollow sphere, and this will represent solid sphere. Initially, it was equal. Let's look at next question. A solid is a copper cube of edge 1 centimeter is suspended in evacuated enclosure. What does evacuated mean? Evacuated means the temperature of the surrounding is zero. We can get zero K only in case of vacuum. Otherwise, so in the empty space, when you travel when you go for space travel, unless you are near to a planet which has atmosphere, in between this vacuum here, temperature will be zero. So solid sphere cube is suspended in that enclosure. So this is a cube which is suspended in enclosure at 0 K. And its temperature is found to fall from 100 degrees centigrade to 99 degrees centigrade in 100 seconds. So basically, if I say 1 degree in 100 seconds, so rate of cooling is 1 degree per 100 seconds or 0.01 degree per second. Another solid copper cube is 7 centimeters. So this is two identical cubes. One is 1 centimeter and second one is 7 centimeter. This is a larger cube. This is 7 centimeter. And this also similar surface, it is suspended in a similar manner. What is the time required for this cube to cool from 100 to 99? So this one from 100 degrees centigrade to 99 degrees centigrade for delta temperature. What is delta T here? Delta T is equal to 1 degree centigrade, which is also equal to 1 K. That's a drop in temperature. And this has taken time of 100 seconds. The question is how much time this will take here. How do you find out? Well, that's it. That's the case here. So what we understand, again, we have to keep in mind, not the entire formula. What we understand, the rate of cooling is this part here is same. This part in both cases are same. Only thing which are the parameters varying, same material here also same. So here only parameter which are different is surface area and mass. So I can write rate of cooling is proportional to surface area. And the mass is also proportional to volume. So it is proportional to, and since it is a cube, I can write area is equal to what? Area is equal to proportional to 6 L square, and volume is proportional to L cube. What I find here, this all such cases, several other things are changed, which are changing the ratio type of question. I need to find an equation between. So when I look at this question, I notice only thing which is different is size of the object. So I must find a relationship between rate of cooling and linear dimension. So what is proportional to the rate of cooling is inversely proportional to linear dimension if shapes are same. So that is very simple. If the dimension becomes 7 times larger, rate of cooling becomes 7 times slower. It will take 7 times more time. So if this is taken 100 seconds, it should take. So as the change temperature is small, we can assume the rate of cooling to remain constant during time interval. And rate of cooling is proportional to A by M. Time taken will be inversely proportional to rate of cooling. So rate of cooling will become 1/7 time. As time taken will be 7 times more. If it has taken 100 seconds, that will take 700 seconds. Okay, next question. Read the question first of all carefully. See what you have understood. In solid copper sphere, density is given, specific heat capacity is given. So you have a solid sphere. Okay, so copper sphere, density copper radius R is given. This is initially at 200 K. And is suspended in chamber whose walls are at almost 0 K. This also either if the word could have been used, it is placed in vacuum. Vacuum, whenever you come across vacuum, temperature of the surrounding is 0. That's given here. Question what we need to calculate time required in microsecond for temperature of the sphere to drop to 100 K. From 200 K to 100 K, how much time it will take? We have to find relationship to these parameters. Okay. So again, in this case here, is here unlike can we apply Newton's law of cooling here? We cannot apply Newton's law of cooling, but the rest of the things are applicable. We will not apply Newton's law of cooling, no heat will be absorbed from the surrounding. So only loss of heat due to radiation. So we'll just write an equation between the two for a small time interval dt. This is the loss of heat, this is the radiation. Since this is the loss of heat, just note the terms of very similar term, nothing new are written. That is equal to minus mc delta t. This is, I think, whenever we cannot use standard equation, and anyway, there's nothing to memorize here. This is very simple. This is heat lost in time dt will be equal to mc delta t change in temperature. Now, since here all the parameters are given here, let's write all those terms here. Basically, area is we have written area term here, temperature written here, and we have written this mass, density, mass into all this term. So basically, it gives you relationship between temperature T and time. That's what we need. We relation as the time changes, the temperature also will keep on changing. Once we have relationship between temperature and time, we need two values of temperatures are given, 200 and 100. So if we integrate the limits for temperature, initial value 200, final value 100, I can find out delta small t, which is time interval. So can we easily do it? Very simple integration. So I will not do it now. So all of you can easily do that integration and find an answer. Only thing, if you substitute everything, whenever such questions are given, we assume everything SI unit, we find the answer, it will come in terms of seconds. So we multiply by 10 to power 6 to get in microseconds. Okay, and other thing what we need to assume here is another thing. We understand how does Earth receive energy from sun in form of EM radiation. And this we have, I think we have dealt with this particular concept even in other topics as well in second year, some of the topics. So let's understand again, how is this related? And there's some important point to be understood from this example. Earth receives at its surface radiation from the sun at the rate of 1400 watts per meter square. We use some other term also for this. What is the term we use for something like this? Energy per unit area per unit time. This term is intensity. We have come across this term intensity in number of cases. Intensity we use also in case of sound energy. And for intensity, whenever I have to calculate intensity at particular point, so whenever in calculation, we take the area to be perpendicular to direction of radiation. So this is the energy. This is another way of saying this is intensity of radiation from the sun at a distance equal to at r equal to distance between sun and earth. And what is this intensity here? So distance between sun and earth is given. So this r value distance sun is given, and radius of sun is given here. What are things given here? A distance between sun and earth is given, and radius of sun is given. So let me call this one as radius of sun r. So treating sun as a black body, based on this information and assuming that Stephen Boltzmann law to be correct, can we calculate what is the temperature at the surface of sun? Let's do that, and we work back here. What is available? We know what is the intensity on the surface of Earth. From surface of Earth intensity, we have done it earlier. We can calculate power radiated from surface of sun, and power term can be, if power is there, if this is in form of radiation, power is related to surface area and surface temperature. So hence we get the surface area term, hence we can find out radius. Intensity to power and power to surface area, for surface area to radius of sun. And surface temperature. Well, this all those things we can relate. Let's write the sun as a perfect black body. What is the power of heat radiation? What is the energy radiated per unit time? That is nothing but power. Unit comes into rate of heat radiation is power. And if it is perfect body, that's a E is equal to 1, Boltzmann constant, I square, R being the radius of the sun, into surface of T square. So that's the power radiated. Intensity on the Earth's surface is equal to power by 4 pi small r square. And this value is given. This value is given as 1400. And if I could link these two terms here, you notice here all the terms are there, radius of sun, everything is there. We can find out temperature on the surface of sun. So one important point what also you need to understand here is, suppose we keep up any object here on the surface of earth. So this object, we keep any object which is also exposed to sun radiation. It is also exposed to radiation from sun. And let's see if I can take a simpler case. Okay, let me just, so let me again redraw. So basically, if I keep a kind of plate, and this plate is placed in a, this plate has a temperature T. It is placed in on near the earth's surface where air temperature is T naught, and it is not inside the room. It is kept out in the open, so it is also exposed to some radiation. Sun also radiations are reaching. And area of plate is A, and it is kept perpendicular to radiation. In this case, if it is perfectly, in this case, if it is perfectly black body, if I have to calculate what is the net rate of heat loss, if I have to calculate. See, we have done earlier, we have calculated net rate of heat loss to be equal to sigma times Steven Boltzmann constant, area of the object, T4 minus TO4. This does not take in account any radiation falling onto the surface. So whenever radiation like this falls onto the surface, I need to add this minus here, where this radiation coming, minus the power of, basically this energy also I need to add. So I need to subtract, what is the term I need to subtract here? Intensity here is I naught here. In addition to this loss, it will also okay, sorry, let me write this term again. So what are the energy it receives? Energy received will be equal to sigma A T naught 4 from surrounding medium. In addition to this, this also receive energy equal to E times area into intensity of radiation incident. This is additional radiation energy it will receive. That's all only thing we need to keep in mind. And what is the loss here? This is from radiation. You have to understand radiation energy received is different from energy absorbed from the surrounding. Radiation is come because of EM radiation is coming, something like sun. So if we keep it in the sun, in addition to these two terms, this additional term will come in. That's all. And we see one or two questions where something of this nature has come. Otherwise, this kind of application not had come so far. But a similar thing is there. We'll come to that question. Just keep that in mind. And it makes common sense. So when we talk this term here, this is not due to radiation. This is because surrounding medium air molecules come in contact with the object, they transfer energy. So this energy is not coming in form of radiation. This is coming because of context also radiation. The steady state temperature of Earth or any planet. So suppose we take this case here. See, but we know that different planets, even on the Earth also, different parts of the Earth is at a different temperature. So I'll add in one more concept here. Is it possible if I assume Earth is not, if we assume two assumptions I'm making here, and let's understand two assumptions are helpful in understanding few more things. If I assume Earth to be perfectly black body, one part, and I assume Earth to be a very good conductor. What does good conductor mean? K value is very high. Whenever thermal conductivity is very high, what does high degree of thermal conductivity mean? I discussed yesterday this briefly. What does very high thermal coefficient of thermal conductivity mean? If object has very high value of K, assume that Earth had a very high value of K, what would have happened? What would have happened? Tejas, can you tell me what would happen if the coefficient of thermal conductivity is very high?
Yes, sir. If it's K is very high, all the both the sides will be almost of the same temperature.
Okay. So
Not temperature.
entire object will be at the same temperature.
Yes.
So this is something, the reason Earth is not having same temperature, the conductivity is not so high. Had Earth conductivity been extremely high, entire part of the Earth, everywhere the temperature on the surface would have been same. So if I assume, if K is very high and Earth is perfectly black body, entire Earth would have been a constant temperature. And if we make an assumption, can we calculate what would be temperature of Earth? Yes, that can be calculated. So what would be for a steady state temperature of Earth or any planet? How would I calculate? It will reach a steady state when net rate of radiation is zero. It is not radiating. So water heat is receiving, same amount of heat is radiating. So energy received here will be equal to water. So temperature at which rate of heat radiation per unit area is equal to intensity of radiation from the sun. If these two becomes equal, at that temperature is the steady state temperature of the Earth. So whenever a steady state is required to be found, that's how we'll do it. And that's why I'm not solving any question. This is just to make you understand what does steady state temperature of object mean. Steady state basically means net rate of heat transfer is zero. And in case of Earth, only way it is receiving Earth, basically surrounding air also we are taking the part of Earth. So it is receiving energy in form of radiation from sun. And at a particular temperature, if I have to write it equation, temperature. So what is the rate of heat radiation from the sun, from the Earth in that case? Okay, let me just write the equation also. It will be sigma. Area will be equal to 4 pi Re square. Before, what with this temperature? This would be the steady state temperature. This has to be equal to intensity into which area square? Pi Re square. I think all of you, some of you should remember. What is the heat which should be incident on the Earth? Not 4 pi R square. It will be like a circular point. So this equation give me the steady state temperature of the Earth. If I assume Earth to be a perfectly black body and be a highly conducting object. And something similar, let's look at this question. This also is one of very good question, a little different question. As a past advanced question, let's see that. Well, let's understand here. And it's very good to understand the basic concept here. Three very large plates of same area, very large plates. So large plates in basically, whenever we talk about large plates, we always ignore the end effect. We only focus on the middle part. We do in capacitor and so many other cases. So end effects are ignored. The end with the symmetry is lost. So palladi are kept close to each other. They are considered as ideal black surfaces. So three plates, you paint it black, you keep them black, and they have very high thermal conductivity. What does very high thermal conductivity? It's not all parts at same temperature, different parts of the surface. Everywhere temperature in the object is same. The first and third plates are maintained at temperature. This is 2T. This is maintained at 3T. Maintain means what? We have some way we can supply or take away heat such that temperature does not change. Okay. So we temperature is maintained. Right? So they are in contact with other heat source. So they are not thermally insulated. They are receiving heat or they can give a heat. But the middle one is not maintained. The middle one is just placed there. So what is the steady state temperature of the middle plate? So if I keep two plates at the constant temperature on either side and middle plate, what will be the steady state temperature? The moment I look at this question, what will happen? You can imagine if the plate is kept between two heated surfaces, this plate also will radiate. Is not talking about certainly this plate will radiate heat. This side also, this side also. So this plate is radiating heat, and they're all black body. Whatever heat is radiated by right surface of 2T, it is incident on the left surface of the middle plate, and whatever heat is radiated, everything will get absorbed. So it will receive heat. Left surface of middle plate will receive heat from 2T plate. Right surface will receive heat from 3T plate. It's receiving heat. And so it will receive heat radiation. And that is the net heat it receives here because the radiation on this side as well as this side. In addition, if its temperature is not zero, which will not be in the steady state, it will also, when it reaches steady state T naught, it will radiate heat. What has to happen here? Net rate of heat radiation has to become zero. What is the temperature T naught at which the net heat received is equal to net heat radiated? That's all we need to do. Let's now apply this one. So plate N, A and B, will I call this plate A and B, will emit EM radiation. half the radiation because of one side will be absorbed. So what we'll do now, we'll focus this, since the large plate, we'll focus only on, okay, so half the radiation will absorb by C. Steady state condition, rate of heat absorption is equal to rate of heat radiation. Now consider unit area of plate C. So basically we'll focus only in middle part, which area. So I take a section which encloses unit area of this plate, this plate, this plate. So what is this air surface area? It is in perpendicular to the figure also. Everywhere area is 1 unit. So we are concentrating only in the part which is enclosed here. Okay. So okay. Rate of absorption of heat by unit area of C. What is the heat it will absorb? It will absorb heat equal to sigma into 2 to the power 4. This unit area, see, basically this is equal to heat radiated by 1 square meter of right surface of 2D plate. Is it not? So 1 meter, whatever heat is radiating from here, since it is perfectly black body, same amount of heat is absorbed. So this is the heat radiated by right surface. Left surface heat will not receive here. So only I'm taking one area. So E is equal to 1 here. Area also is 1. So E into 2 to the power 4. This is the heat radiated by right surface of 2D plate, and this is the heat absorbed by the left surface of C plate. Similar way, the heat radiated by left surface of 3T surface will be equal to sigma into T. Sorry, I think this is 3T4 here. This is 3T4. This is 3T4. And this heat radiated is sigma into 3T4. And whatever heat radiated is absorbed. So this is the rate of heat absorption per unit area of C, both sides. And if its equilibrium temperature is T naught, what is the rate of heat radiation? So I have written something, just all of you can notice what is missing here. Can someone notice net of heat radiation per unit area? Is this term correct or something is missing? Anyone notice what is wrong here? I have taken what area? Surface 1 area. So there's something wrong. This is something. Can someone notice what is missing here?
There's emission on both the sides, right, sir?
Yes, emission is on both sides. So basically what I need to do here, I multiply by 10. So it is absorbing from one side. This is something, just see that how the equations are formed. So all I need to multiply this term by 2, equate those two, I get the value of T naught. So this is the question. And in this case, nothing to with the surrounding. And this is something like some system similar to sun and earth kind of system. Okay. You get the rate of heat radiation to rate of heat absorption, you get the value of T naught. Okay. Next one. Black color solid sphere of radius r mass m inside a cavity with a vacuum inside. And this question also had come, and okay, there is some flaw in the question also. Let's try and understand. And some of the question which comes in mains also. Some of the questions are you need to make some assumption to solve. That's why I keep telling all the question may not be perfect, but if the question comes in whatever form, you need to make some common assumption. You need to think what way it can be solved. That assumption you need to make. Let's see that what the question is. A black color solid sphere of radius r, mass m inside a cavity with vacuum inside. So let's see that one. If you have to visualize a figure, this is black solid sphere of radius r, mass m. It's inside a cavity with vacuum inside. So this is placed inside a cavity. So there's a cavity here, and there's a vacuum here. Space between inner surface of cavity and outer surface of the solid sphere is vacuum. Walls of cavity are maintained at temperature T naught. This cavity wall's temperature is T naught. The initial temperature of the sphere is 3 T naught. If the specific heat of the material sphere varies as TQ, what is specific heat of specific heat also is not constant. We realize C term is not constant. C also is a function of temperature. So as the temperature keeps changing, the specific heat capacity also is changing. And what is C? C is something, C is proportional to TQ per unit mass. Will the temperature. So different temperature value C is changing. What is the time taken for the sphere to cool down to temperature of 2 T naught? It is 3 T naught. This is T naught. After the temperature start falling, this temperature is not changing. This is maintained at T naught. How do you solve such question? And you notice some of the question which used to come in mains in 14, 15, 16, 17, they used to be as tough as advanced question. Now only mains have become simpler. So that's why you will notice question which have come 4, 5 years back. Some of the questions were quite tricky and they're not so easy to solve. And yeah, so this is something. So have we done today something similar like this? We had done one question where the temperature difference was varying. So again, what we take, since the temperature difference is varying, this is not changing. This temperature is changing. So I'll take a particular instance when the temperature is T and then see what happens. Basically, in this case, whenever it is changing, we have to take the net heat radiated in time delta T when the temperature is T. I take a random state when this temperature. So I'm finding a random temperature T of the object. And what is the net heat radiated in time dt here? The net heat radiated is rate of radiation into time. Rate of radiation is equal to sigma into 4 pi square T to power 4. That's the temperature of the object, and surrounding temperature is T naught, T to T naught raised to power 4 into dt. That's the heat radiated in time t, and that is equal to minus mc dt. And if you look at this equation I have, this is maybe third or fourth time we are talking about today. This is important part of equation to solve question which are of medium to high level difficulty. That's the equation. And once I write this equation here, okay, so can we, what else I can substitute here? Okay, now let me put some more terms here. What are the terms we have known here? Mass, okay, mass is given. Mass, we can write density into radius. Only thing, what is the C term here? C term also is not a constant. C also is a function of which one? It is a function of T. C term also I could have written a constant in TQ. If you write that without constant also, the answer comes in as ratio. So C term I would have written it's some proportion to TQ. I get a equation. Once I get this equation, can I find the time taken for temperature, which is changing now in this equation? We need to find delta T time interval corresponding to what? Corresponding to T changing from where to where? T is changing from 3T naught to 2T naught. So I'll arrange this very simple, two variables, and I integrate with appropriate limit. I can find the value of time taken. Now, if some of can notice what is little bit wrong in this question.
The temperature difference is big, right?
The temperature difference we are taken care of. Temperature difference we are taken care of. The temperature difference is written here. Something else which is wrong. Okay, I'll just skip it now. Some of you think and tell me. I think I'll discuss separately because most people get confused. So so if I strictly look at this question, yeah, this is how I would have solved this question had it come in the examination. That's only appropriate assumption I made. If you start examining critically, I find there's some small flaw in the question, which I'll discuss little. If somebody is interested, you can spot that one. We'll discuss later. I'll not confuse everybody with that. Try to spot what could be slightly off in this question compared to previous question. Okay, so
Sir?
we can, yes.
So we don't include conduction in this case, right?
Where's the conduction? Tell me. There's a
Okay,
vacuum.
yeah, vacuum.
Yeah.
Yes.
So that part is not an issue. Okay. But this is some okay. But very quickly, I'll mention. See, if I assume what is not given, what is the radius of the vacuum? Suppose this radius is 3r. So basically, the radiation emitted by inside surface of the cavity will be equal to sigma into its area of the cavity into T naught. And whatever is radiated, that will incident. It will not be T naught surrounding it. So this is something I think the question what they're given was incorrect, but I could have solved. I got what I'm saying now. Okay, leave it. Okay, if you don't get also not an issue. Okay, let's move on to next one. Okay, next one now. So these are the questions related to radiation, and some of the question I have not taken very simple question. I have taken question little slightly tricky, and you see that to the extent possible, all of you try and understand. Most of them are based on this. Mostly we have spent time trying to understand this particular relationship. Yes, Alan?
Sir, I didn't understand the equation, sir. Where do we get t cube from?
This equation you not understood?
In the second one, sir. Where do we
This
get t
equation?
cube? Where you
Basically, see, but the way they have given, what is given, what is C? C is not a constant. When I'm integrate, I cannot use C. Is this C constant here?
okay, yes, sir, I understand.
So C is not a constant. They are written as proportional to T cube, and they are not written as a constant of proportion. Option given also, I could have written some constant. I could assume something like A into T cube. Okay, I can solve that. So is that clear now?
Yes, sir.
Okay, that part only. So this is the only one extra change they introduced, and only thing I need to do when I substitute, I'll get that way also. No problem. Okay, now coming to some of the simpler questions, which are, so in terms of difficult question, you notice both the difficult question. This question also has come to the 14. Since then, I haven't seen most of the questions were fairly easy questions. So questions are like this also. Okay, so a hot body, statement itself mentioned, we have to assume that Newton's law of cooling is valid. It's cooling down from a peak value of 80 to an ambient temperature of 30. It's like a cup of coffee, which is 80 degrees cooling down. It takes 5 minutes to cool down from 80 to 40. How much time it will take to cool down from 62 to 30? Now, this is what up to now what they have done, Newton's law of cooling. Suddenly, what is introduced here? Log values introduced here. So this was how the question was given. And moment I see these values, if these values are known, it implies no approximation. You have to use without approximation. So Newton's law is based on approximation. When law's values are given, how do I solve this question also? So let's look at this. What does Newton law say? Newton law says rate of cooling is dT is equal to this thing. That's why it is minus sign into T minus T naught. This equation. So if I use approximation, I will do in both ways so that you understand what the difference comes in. If these values were not given, I would use approximation. What does approximation says? It is cooling from 80 to 40 degree. First case, it has cooled from, okay, it takes 5 minutes to cool from 80 to 40. Okay. So what is delta? What is the rate of cooling? Rate of cooling is 40 by 5. 40 by 5 is rate of cooling. Delta T by 5. So this is centigrade per minute. That's the rate of cooling. It's equal to K into, where did I get 60? 60 is 80 plus 40 divided by 2. That's what we do. As the temperature of object is changing from 80 to 40, we take the mean temperature. Mean temperature was equal to 60 and ambient temperature was 30. I would have, from this equation, I would have formed. For which purpose? For first stage, from 80 to 40. Then from cooling from 60 to 32, again I'll form equation. What is the rate of cooling? Same unit, how many centigrade per minute? So here cooling is 30 degree, 32, cooling is 30, delta T is 30. And time is T, which we need to find here. That will be equal to, again, K term. K term I find from here. I can substitute K term from this equation here. And K term, and what would I substitute here? This temperature of the object. I take the mean temperature 94 by 2. So that is mean temperature. And I get something like this T. Okay. This is not when log values are given, we need to do something else. I don't have to use approximate, I need to start from here. And when you look at this equation, this is not without approximation, it's a differential equation. It's a relationship between temperature of the object and time. Okay, and this is what we need to find here. So if I need to do that also, how would we substitute here? I'll use this equation, and this equation, it becomes like this, dt by t minus 30. This term is not changing. 20 by 30 is equal to 5, a negative sign here. And first case, what are the limits? First case, initial temperature is 80, final is 40. I just substituted in this equation the values which are given here, 5. And from here, I find the value of K here, the constant of proportion. And then I use the second part. This is first part is cooling from 80 to 40. Now I found 60 to 32. Again, I substitute 60 to 32, same integration, and k delta t here, and k value I substitute from here, and again I can calculate what is the time it will take, and that comes to 8 point something. So see that both parts are understood. One is how do we calculate using approximation. Both ways we are doing what? We are substituting this cooling 80 to 40 cooling, and when we substitute 80 to 40 cooling, we are finding constant of proportion, and then we are using second stage cooling from 60 to 30. So when we do approximation, temperature of the object, and when we do approximation, we take average temperature of the object here, average temperature of the object here. That's what substitution we make here. But when we do integration, rather than substitution, we substitute as a limit of integration. That's all. And since the value of logs are given, we can solve. And all this question, is something all of you need to solve on your own and see that is all understood. Okay, so this is something about Newton's law of cooling. I'm not doing any simple question because those questions are straight application of formula. So all of you, I'm sure, we can do that. So we can, and I have given one idea. This is something. This all question on Newton law of cooling. Except for this question, very rarely you come across question. Very few times the question have come on based on integration. So we are done in both ways and see that both ways are understood. Okay, so this is the related to radiation, and after radiation, this is small part which is called Wien's displacement law. What is Wien's displacement law? Is something any object. See this some whatever object means. If we can take a steel ball, even if it is not heated, any steel ball which is lying at the room temperature also, if it is at room temperature, see suppose something like 300 K. What the Stephen Boltzmann will say, even at any temperature which is greater than 0 K, it's radiating EM radiation. What is EM radiation? EM radiation, we should understand EM radiation will have particular wavelength, it will have particular frequency. Speed is same as speed of light. When you have EM radiation, then naturally the question comes, the different object when it is 100 degree, which wavelength it will radiate EM radiation. So, so to understand this, and this is Stephen Boltzmann law tells you what is the amount of heat it will radiate in a given part of time, or what is the heat of radiation. It doesn't tell you what will be the composition of radiation in terms of wavelengths. This displacement law tells you some idea about what those wavelengths are. And to understand that part, we need to think of sun. Sun also is like we imagine the sun as a black body, and sun is a heated object at a fairly high temperature, and it radiates EM radiation, and EM radiation as it travels from the surface of sun to any planet or anywhere else also, the wavelength that is keep changing, wavelength is not changing. Whatever wavelength is radiated, it reaches our earth also. And why we have understood, if those radiation, if we make it pass through a prism, what we find different wavelengths. When we have this kind of scenario, what we are, a simple example makes us understand that wavelengths radiated by sun is not one particular wavelength. It is several wavelengths. And this is something part of it what we can see. In addition to this infrared rays also, there is ultraviolet rays also. It emits radiation of several wavelengths. Okay. Okay. So I'll just stop here for a minute. I think it's almost time. I'll continue after the session. I'll take a small break and then continue.